Hello, this is Liz here from Maths for Granted, and today we are looking at A-level proofs, and in particular we're looking at a proof, as well a style of proof that you will probably meet more in your second year of A-level at year 13, something called proof by contradiction. So by the time you meet proof by contradiction, you've probably already met proof by deduction, proof by exhaustion, and disproving with counterexamples. So this is perhaps a slightly harder type of proof, but it is very enjoyable once you've got the hang of it and you get used to the different stages of a proof by contradiction. So let's have a look at a few examples. The examples we're looking at are very famous examples, and I would probably learn them off by heart, because you may well get one identical to this or very similar to some of these. Okay, so let's look at the structure of a proof by contradiction. So to prove a statement is true by contradiction, first of all, we assume that the statement is in fact false. Prove that this would lead to a contradiction. So, it ends up being complete gobbledygook and it doesn't make sort of any sense, and you end up sort of proving the opposite. It's not quite opposite. Therefore, we were wrong in assuming the statement was false, and therefore it must be true. Okay, let's look at a very straightforward one just so you get the idea of how to set them out. So here is our first one. Prove that there is no greatest odd integer. So the assumption is a contradiction of that. Well, a contradiction of that there is no greatest odd integer. The contradiction of that, the negation of that, is that there is a particular odd integer that is the greatest. Assume that there is a greatest odd integer n. Well, if we have an odd integer n, of course we could easily add 2 to that odd integer n, and obviously what happens when you add 2 to our greatest odd integer, it would be larger than n, and of course we know if you add 2 to an odd number you will still get an odd number. So this contradicts the assumption that n is the greatest odd integer, and we usually end on a therefore there is no greatest odd integer. So you normally restate the original statement. So here's the basic structure. Assume that, and then you say the negation of the statement that you're given. Now, it's not quite the opposite you will see. It's a negation. So we'll look at some examples. Then you go through some sort of reasoning, and then you end up saying this contradicts the assumption that, or this is a contradiction, and then you generally restate the original statement. So therefore, there is no greatest odd integer, for example. Okay, so let's have a look at this idea of negation. So some students don't always get the correct negation. So let's have a look at some of these. The latter two you won't actually get, but we will look at this one in a bit more detail later. There are infinitely many prime numbers. So you've got to think of the negation of that, the contradiction of that. So let's have a think. So here are our choices. There are infinitely many non-prime numbers. There are finitely many prime numbers. That means we get to a particular prime, a really large prime, and there aren't any more prime numbers bigger than that. There are finitely many non-composite numbers. Okay, so hopefully the negation you've spotted is this second one. So if I want to find the contradiction of infinitely many primes, I'm going to contradict that with there are finitely many primes. Now let's look at the next one, because this could be easily misunderstood. All popes are Catholic. Now I'm not looking for the opposite of that, I'm looking for the negation of that, a contradiction of that. So there exists a pope who is not Catholic, no popes are Catholic, Dr. Frost, who writes these PowerPoints, is the Pope. Well, that's just a silly one. So in fact, it is the first one. And the second answer, some people might have gone for. So let's have a read. The negation of all are is not none are. So, for example, the negation of everyone likes green wouldn't be no one likes green, but not everyone like green. So here, all popes are Catholic. We would say not all popes are Catholic, and you've only got to show that there exists at least one. Okay, let's look at this next one. If it is raining, my garden is wet. Let's have a look at the negation. It is not raining and my garden is dry. It is not raining and my garden is wet. It is raining and my garden is not wet. It is actually this third one. And listen to the style. If you have something like if A then B, like we have here, if A then B, the negation of that is if A, if it is raining, then my garden is not wet, so not B. Okay, so be careful of that sort of style. So let's have a look at some common examples. I think we're going to look at 3. Prove by contradiction that if n squared is even, then n must be even. Okay, so it's a little bit like that last one. Remember the negation of if A then B is going to be if A then not B. So here's our contradiction. If n squared is even, then n must be not even, which of course we call odd, don't we? So here's my assumption. Assume there exists a number such that if n squared is even, but n is not even. So of course here we're talking about odd numbers. So that means that if n is odd, then we've seen at GCSE and some previous proofs, then we can always write an odd number. If k is an integer, we double k, which would make it even, and we add 1. So I know n is definitely odd here, isn't it? N equals 2 times an integer, add 1. So when we get n squared, you will obviously have to square all of that. Imagine your double bracket expansion, and you would get 4k squared, add 4k, add 1. Now, to show if something's odd or even, we want to try and take a factor of 2 out. Well, you can take a factor of 2 out of these first 2 terms, 2 lots of 2k squared, add 2k, which means this bit here is even, isn't it? Because it's 2 times something. So this is in your 2 times table, so it's even. But look, I've still got a plus 1, which then makes it odd. So if you start with an odd number, n squared is odd, which contradicts the assumption that n squared is even. And remember how we finish them off? Therefore, if n squared is even, n must be even. So they're always that style. Assume, then you do some sort of method, and then we say this contradicts the assumption, and then we do therefore, and then state the original statement from the start. Okay, let's look at a really famous example. I didn't meet this until second year of my maths degree. So I know some people say A-levels have got easier, but of course we just changed the content over the years. So now proof has come heavily into A-level maths. So this is a lovely one to learn off by heart because you might get a similar style. Okay, prove by contradiction that root 2 is an irrational number. So you need to understand what an irrational number is. So a rational number is a number that can be expressed in the form of A over B. So it can be expressed as a fraction where A and B are integers, and we should say, you'll see in a minute, that this fraction can't be cancelled down, it can't be simplified. So an irrational number is a number that can't be expressed as a fraction where A over B are integers and cannot be simplified. So you have already met a few types of irrational numbers, pi, e, root 3. You don't really need this in this question, but it's worth remembering your set notation. So rational numbers, we use the letter Q. Real numbers, which include rational and irrational numbers, we use the letter R. Natural numbers are our counting numbers, so 1, 2, 3, 4, 5, 6, 7, they're our natural numbers. And integers include positive and negative natural numbers, and with 0 also. Okay, so we don't really need that, but worth remembering those. So we're going to assume the negation of this. We're going to assume root 2 is rational. If root 2 is rational, that means I can write root 2 as a over b, where a and b are integers, and a over b is a fraction in its simplest form. It can't be cancelled down. So let's think what we can do with root 2 equals a over b. So probably square it. There's not a lot else we could do with that, so we could square both sides. So let's have a look. When we square both sides, we'll get 2 equals a squared over b squared, which you can rearrange. You know, you could times both sides by b squared. We'll get 2b squared equals a squared. Well, let's have a think what that means. 2 somethings, bearing in mind b is an integer, so b squared will be an integer. So I know 2b squared is going to be even, which means a squared is even. And there is a proof that we've perhaps seen in proof by deduction that if a squared is even, that means a has to be even. Okay, so if a is even, we can actually write a in the style of 2k, where k is just an integer. Okay, if a is 2k, let's go back to this statement here. If we square 2k, you will get 2k all squared, which is 4k squared. So now we're saying 2b squared equals 4k squared. Well, you could divide both sides by 2. So now we're saying b squared equals 2k squared. But 2 somethings, this is an integer, must mean b squared is even. So now we've already said if b squared is even, we know b is even. So now we have just proved that a and b are both even. Well, if they're both even and you write a over b, that means they are not fully simplified because they obviously have a factor of 2. They're both even, so they haven't been written as a fraction in its simplest form, which is what our assumption was here. So this obviously contradicts our original assumption, which we perhaps should say, and therefore root 2 is irrational. So that's a really good one to learn, the structure of that type of proof. Let's look at one more, another really famous one, a proof from Euclid a long while ago. Proof by contradiction that there are infinitely many prime numbers. So we talked about this one earlier. So the negation of that is there'll be a finite number of prime numbers. I will get to some sort of large prime number, and I'm assuming I can't find a prime number bigger than that. So assume that there is a finite number of prime numbers, so we could sort of list them all. So my first prime, we'll call it P1, well we know that's 2. Our second prime, P2, well we know that's 3. Our third prime is 5, etc. And I get to some sort of big prime, and I'm assuming there's no prime bigger. I've just Googled, for example, a nice big prime for us here, 24,738,041,398,529. So I'm assuming that is the biggest prime number, and I can't find a prime number bigger than that. So let's see what happens if we assume this is our biggest prime. Consider we have a number, let's call it n, where I make n by timesing together all of the primes that I believe exist, you know, 2 times 3 times 5 times 7 times 11 times, up to that number I just said, 24 trillion, etc. Assume you can have a number then, all of those primes times together, and then I add 1. So can you see what happens? If you try and divide n by all of those primes, there'll always be a remainder of 1, which means n is not divisible by any of those prime numbers. So n must be itself prime, or in its prime factorisation that you make at GCSE, there contains only primes not in our original list. There must be another prime not in this list. So this contradicts the assumption that I've got a finite number of primes contained in the list of all prime numbers. So there's my contradiction, and remember we say therefore there are an infinite number of primes. Again, that's one I would learn the structure of. Okay, hope that's helped. We've gone through a few examples. With all of these, I'd practice a few different types. Make sure you've done all of the examples in your textbooks. Hope that helps. Thanks to Dr. Frost Maths for that PowerPoint. See you again soon. Bye.